Hi, welcome to Efficient Transformers, a survey. My name is Shamoon Siddiqui, and I'll be walking through this paper. So first, we note that this is in fact a survey paper. So they are not claiming any novel contributions, nor are they showing any new innovation. Rather, the objective of the survey is to study other papers and other work that has been done in an attempt to make transformers more efficient. First, we note that this is a relatively recent paper with a publication date of September 16th, 2020. The date of today, February 1st, has about 17 citations. There are 4 authors, Yi Tae, Mustafa Degani, Dara Bahri, and Donald Metzler. They are all from Google Research. So first, we consider what exactly a transformer is. It's a new architecture developed in 2017 by Vaswani et al. The original transformer was designed to solve the task of neural-machine translation, specifically from converting text from language A to language B. It can be used to many different kinds of sequential data, not just language, and in fact, it's also been applied to spatial data, images. When it comes to sequential data modeling, previous state-of-the-art utilized recurrent neural networks and variants like LSTMs and GRUs. What made transformers take off? There's a few different things. So it took away this idea of recurrency and focused only on attention. In fact, the original transformer paper was titled "Attention is All You Need." So given that it's a purely attention-based model, it's able to pinpoint the specific parts of the sequence that matter to other parts of the sequence. Second, the entire sequence is processed at one time, so you can have parallel computations for the entire, in this case, a sentence of data, which helps avoid backpropagation through time, which is a common mechanism for RNNs and variants. So backpropagation through time requires the error propagate back one time step, calculated, then another time step, and so on and so forth sequentially. It's very expensive to do this, and transformers have done away with this. So as wonderful as transformers may be, they are, of course, not perfect. They suffer from many problems. The biggest problem is computational complexity. The attention matrices can become very expensive to compute. The memory can become very overwhelming. In the case of GPT-3, we have 175 billion parameters. And as the sequence length increases, the attention mechanism continues to grow in complexity, actually at a quadratic rate. So self-attention complexity, it's a graph-like inductive bias, and basically that connects the various tokens in a sequence together. So if we have a sentence, I went to the store to buy food, it will create a graph that maps out how each of those words maps to each other word. That is scored based on relevance, which we call attention. But as mentioned before, this suffers from quadratic time and memory complexity. So although efficient transformers is not a specific paradigm or architecture, it is a class of architectures, the goal of which is to fundamentally reduce computational or memory complexity. If we can do that, we're able to train much faster. We're able to have larger models, like we saw in the case of GPT-3, and we can process even longer sequences, again, as in the case of GPT-3, where we can process sequences and have words that are hundreds of words away or thousands even from some original point, and calculate how they'll impact the rest of the sequence. So the paper, the survey paper, uses this term X-former to refer to a series of transformer-based models that have come up, and they, nomenclature-wise, tend to follow the blank former paradigm, reformer, linformer, so on and so forth. The survey paper, the authors attempted to come up with a taxonomy. The taxonomy is crude. It is there's a lot of overlap, as we can see here. So the 5 large buckets are X-former architectures that involve low-rank or kernel-based methods, fixed factorizer random patterns, memory compression, learnable patterns, or recurrence. There is considerable overlap in these buckets, in these groupings. All of them, however, intend to apply sparsity to that attention mechanism. Given the density of that attention mechanism, the goal is to make that as sparse as possible to reduce that complexity. They do this by approximating the attention matrix where they can, as opposed to calculating it every step, every time. And they have many different ways that they accomplish that, and we'll go through a few of them. So now we begin with a brief walkthrough. So a quick caveat, because they covered quite a few architectures, we will only be touching on a few of them to demonstrate the various approaches taken to making transformers more efficient. So amongst the first that they reviewed fall into the local and fixed patterns model. So we have the memory compressed transformer and even the image transformer. What they share is instead of having attention be applied to the entire sequence, they localize it. So as an example, if we have that sentence again, I like to go to the store to buy food. Rather than thinking about how the word food relates to the word I, we can localize it and say we only care about the preceding and 5 words, 10 words, whatever the case may be. This helps reduce the cost of attention in both cases. In the case of image transformers, it can either be one-dimensional, as in the case of sequences, or two-dimensional, as in the case of images. The memory compressed transformer also reduced the number of queries and keys by having strided convolutions. So rather than going one at a time through the sequence, by having a stride, they can reduce some of that. And you can see the complexity lowers from quadratic to less than that in both cases. One thing to note is the global receptive field is in fact lost. So in the example of I like to go to the store to buy food, we no longer have any context of food relating to I. In some cases it may not matter, in some cases it may. So use at your own discretion. The next set of architectures are combination ones, starting with the sparse transformer in 2019, where it, instead of using strictly local attention heads, they use local attention heads for half of them and stride attention heads for the other half. This helps reduce the density of the attention matrices while maintaining some degree of global context. The axial transformer is very similar to the sparse transformer, the difference being that it is an encoder-decoder architecture, and it splits up the matrices axially and applies attention to a single axis as opposed to the whole matrix. Sparsity continues with the long former. It's the same concept as the sliding windows, but instead of sliding, we can also dilate. They also retain certain global tokens for specific tasks. So in the case of text classification, we can say, it will retain the position and the global token of start of sequence or end of sequence. This reduces complexity from quadratic to linear, where whatever the window size is what we're constrained by. The extended transformer construction, or ETC, applies several attention mechanisms versus global to global, global to local, local to global, and local to local. The catch here is it cannot be used autoregressively because of that global aspect. The complexity is still quadratic, but no longer quadratic to the sequence length. Instead, it is now quadratic to the number of global tokens. So as long as you keep the number of global tokens small, start of sequence, end of sequence, and whatever else might be relevant, it doesn't grow quadratically. Another class has to do with really parameter sharing. So with local sensitive hashing, it makes the transformer layers reversible, and it shares parameters between queries and keys. So as a result, there's fewer parameters than a normal transformer, and the memory complexity is reduced from quadratic to n log n, where n is the sequence length. So there are several other papers that they cover. The linear transformer, which is a kernel-based formulation. The main benefit here is the inference speed is up to 3 orders of magnitude faster than a vanilla transformer or some of the others that we mentioned. The transformer XL uses segments in its recurrence, so it can compute a little bit in parallel. But because of those segments, it needs a relative positional encoding as opposed to absolute positional encoding. So that being said, there are a handful more that we've not covered, and perhaps we will in a future video. But one thing to note is the difficulty that they had in evaluating these transformer architectures against each other. So first is, although there are a handful of standard tasks like machine translation, or in the case of images, image classification, many of the architectures use their own benchmarks. So there is not a fair comparison to say which is or isn't better for a particular task. The hyperparameters matter a lot with most neural networks, with most deep nets, with transformers especially so. And the choices that the individual authors made, sometimes empirically, don't lend to easy evaluation between various architectures. So with that, I thank you. And if you have any questions, you can get in touch. There's my email provided. Thank you.